So in this module, we're going to talk about the binary eutectic system, but we're going to work a couple examples with these problems. So let's look at the first one first. So as always, this is going to be on the quiz. So go over to the quiz after you hear the prompt and then answer it and come back and we'll go over it. And then also we'll start with the other question after. So we have a 5 weight percent silver remainder, so 95 weight percent copper alloy. So this is the precipitation hardened alloy. And I want you to calculate the weight fraction of beta precipitates in the alloy at 300 degrees. So use what we've learned so far about eutectic and also just determining compositions and phase amounts to calculate the weight fractions of beta precipitates at this temperature. So do that, come back, we'll go through this one, and then we'll start another problem after that. All right, so we're looking at a 5 weight percent silver, 95 weight percent copper alloy. So I've tried to replicate the copper silver phase diagram, the eutectic system, here. And this is precipitation hardened. You can see I put the 5% roughly here. So the dashed line. And then we're also looking at what the weight percent beta is at 300 degrees. So 300 degrees is really low. It's basically the one of the lowest temperatures that we see. And it looks something like that. So to do this, right, we know in this region, if we're at this point, we're going to have alpha plus beta. If I can draw that. So that's alpha plus beta. We have liquid up here. We have liquid plus alpha. Sorry about that. Liquid plus beta here. And this is beta. This is alpha. So those are all the regions. So we know that we're in this region with alpha plus beta. And we know that we can get the weight fractions of phases by using the lever rule, right? So we have to do that at this temperature. And so if we draw the tie line, which is on that temperature, and then truncated at the boundaries, which in this case are just the edges, right? So there's what we see is that at 300, there's basically no solubility of the silver in alpha and copper in beta, right? It's because this line comes down. And so basically these compositions are this composition of alpha is equal to 0 weight percent silver. So this means that, again, alpha is just pure copper, and beta is also over here, and it's basically, this is C beta, and this is basically 100 weight percent silver. So basically what this is telling us, because of these lines coming down, it tells us that the compositions of alpha and beta are basically pure, so 0 and 100. So it might actually be some small amounts of each, but from the diagram, the closest we can get is 0 and 100. So we need those lines, and we also need our fulcrum, right, at 5 weight percent. So here, then, we can calculate the weight fraction by applying the lever rule. So for the lever rule, if we want beta, which is the phase over here, we're going to take the opposite length of the alloy composition, which is this length. And to use the previous terminology, we call that length R. And then this much larger fraction was what we called S. So the weight fraction of beta, again, beta is the phase over here, so it's the opposite length, so R. So R over R plus S. And so to convert that into the compositions, that would be basically C naught minus C alpha, and then over the total length, which is C beta minus C alpha, right? So plugging those numbers in, 5 minus 0 over 100 minus 0, right? So in this case, it's simply 5 over 100, so that's 5%, right? Either this or 5 weight percent. So in this case, because we have no solubility of these two components, it's a very simple 5 weight percent. So it matches exactly the weight fraction of the alloy. However, that is not always the case, right? If we do it up here, where there's some solubility, C alpha and C beta can change, and therefore this number, and this number will change, and so it won't be perfectly 5%. So that's something to keep in mind when you look at these problems. So this one worked out nicely, but they all don't work out nicely like that. So pay attention to that when you're doing these problems. But we just have to go with the endpoints of the two-phase field, which in this case are 0 and 100, but up here they can be higher than 0, lower than 100. So that will change this calculation here. So that's what we're looking for this question. So let's go back and take a look at the second question for this, and we will go through that as well. All right, so for our second example question, what I want you to do is, looking at the same copper silver diagram that you have here, I want you to calculate the weight fraction of eutectic solid in a 40 weight percent silver, 60 weight percent copper alloy. So pay attention to the term here. So we're talking about eutectic solid. So see if you can determine the amount of eutectic solid in this alloy. So again, this will be on the quiz, so go over there and see if you can answer that, and then come back and we'll work through this question. All right, so this question is asking about the weight fraction of eutectic solid in a 40 weight percent silver alloy. So I've already gone ahead and drawn this line. So this is our composition. So this is C naught. And it's asking about the eutectic solid. So it's not, the trick here, if there is one, is that it's not asking about a phase. It's asking about the eutectic solid, which is a mixture of phases. But we're still able to use the phase diagram to determine that if we kind of think through how the alloy is forming. So again, if we went up here, right, we showed the diagram, this is all liquid here. And then here in this region, we have liquid, but then we start to form alpha particles. And we form that up until just above the eutectic, at which point we form the eutectic solid. So basically what we can do is we can apply a tie line, and let me switch pen color here so you can see it better. We can do the tie line and apply the lever rule right above the eutectic temperature. And what that will give us is that will give us the maximum amount of alpha. So if I draw that structure over here, we'll have liquid, but then we'll also have alpha particles. And then the liquid here will have, at the very bottom here, right above the eutectic, it will have the composition of the eutectic. And so that means that liquid will go through that reaction, right? It'll go through that reaction to form alpha plus beta, and both of those are at the eutectic. So this is the eutectic solid. And so what we can do here is we can calculate the amount of alpha and the amount of liquid. And what we know is that the liquid will become this eutectic solid. So just below, we'll have the same amount of alpha here. So same as up here. But the liquid that you see is now, all of that liquid becomes the eutectic solid. So we can use that number for liquid from that we're going to calculate above, and we'll know that that will become the eutectic solid below. So let's kind of go through that and work the numbers on this. Okay, so we need the tie line, and let me go back to a third pen. So we are going to do the tie line and the lever rule above. So we need this number, which is 8. That's composition of alpha. We need this number, which is the eutectic, and that's going to be the liquid. And then we have our alloy, so we need that one as well. So if we want to know the weight fraction of liquid, then the liquid is over on this side, and so we're going to take the opposite side, right? So that is the length we keep calling R, as opposed to the length over here, which we typically call S. So liquid is going to be the opposite, which is R over R plus S. So again, if we put those numbers in, R is going to be from this to this, or the subtraction of this from this. So 40, or let's put the numbers in here. A C naught minus C alpha over the total length, which was CL minus C alpha. And so those numbers are 40 weight percent for our alloy. Alpha is the composition over here, which we're going to take as the eutectic, which is 8. And then we have this over the liquid, which is the eutectic composition here, 71.9, minus alpha, which is again 8. So if we basically plug that in, what we'll get is this will equal the weight fraction of liquid. And we know that whatever the weight fraction of liquid is, it becomes the weight fraction of the eutectic solid below CE. So this above, just above CE, becomes the weight fraction of the eutectic solid mixture below CE. So that's why we're going to do this calculation. All right, and when we plug this number in, we get that the weight fraction of liquid is going to be 0.501, or that would also be 50.1 weight percent. Oh, let me put weight percent of liquid. And again, we know that that's going to equal the weight fraction of the eutectic solid, however you want to denote it, below TE. So that's how we're able to calculate the amount of eutectic solid in this mixture. So we do it above because we know the liquid all goes to, all this liquid here becomes this eutectic solid, and so we can use that number to calculate this number. So we get 50.1 weight percent liquid, and therefore eutectic solid.